Thank you. I'm Piotr Kulczakowicz. I'm with the University of Maryland Tech Transfer Office called the Ventures College Park. And I will try to cover a lot of terrain today and talk a little bit about entrepreneurship and with a slant towards quantum. Very broad topic. I will focus on some aspects of intellectual property that may be of critical importance for you. I think it's a great opportunity that we are facing today. I don't have a recipe for you to become a millionaire or billionaire. There is not such a recipe, but I want to inspire you. This might be the best time to become a quantopreneurship, as I call it. It's the time when we could compare it to the rise of PC, the internet, the wireless, and related entrepreneurial opportunities. So let me start with saying that quantum startups are real. I mean, Alan was talking about his company Quaxis earlier today. I have a few other names, the Axion Technologies. I was listening to the pitch by this company just yesterday. If you click and go to the website called Quantum Computing Report, where qubits entangle with commerce, they have a list of 209 quantum-related startups and counting. Early stage, huge opportunity. Just hot off the press, perfect timing for today's presentation, and big announcement yesterday by President Pines at the University of Maryland about creation of Quantum Startup Foundry. So real resources are put to support entrepreneurship in this arena. We are only second to Chicago Duality Accelerator program that was launched just 2 weeks earlier. To our disappointment, we were hoping to be the first in the country. So let's talk a little bit about a startup. What is a startup? I mean, it starts typically with an idea, right? Or technology. And it's a new company that is experimenting, trying to find a way to build a product or service that would bring value to the marketplace. Just an idea is not enough. You have to have a team that is dedicated to the effort, and you also need money, or initially at least time, and as we know, time equals money. I call it 3 T's for team, tech, and legal tender. What I'm going to be talking about today is specifically the tech side of things, especially in the quantum arena. It's so nascent. I mean, quantum has been with us, as Patrick was telling us earlier today. Lasers, we're talking about 50s or 60s. But quantum computing, some of the quantum sensing technologies, quantum networking and communication and then so on, this is emerging, right? And the focus of this presentation is going to be on the tech side of things. But again, the startups are built on intangible assets. So it's typically a strong team with certain skills, with a good idea, and for a product, in this case, most likely has to be very anchored in the deep technology and new technology at that. So when we talk about intangible assets and we focus on intellectual property, we're really talking about 4 types of intellectual property. One is in the form of patents. You describe your invention and you make it public in exchange for patent claims that allow you to keep the monopoly on your invention. It's a great tool, but most of the patents don't make any money. However, for startups, and especially in quantum space, I think patents would be extremely important. There are other ways to protect your intellectual property, those intangible assets on which you build your company, your nascent, newly born company. Again, Quaxis earlier today was one of the startups talking about their devices. One of the intellectual properties they have is trademark, a brand name, if you will, and everything that goes behind it, the reputation for quality and then the innovation, things like that, right? Another type of intellectual property is trade secret. Google algorithm is a very closely held trade secret. We don't know exactly how it works, but we know that it works very well. Instead of going open, as you would do in the case of a patent, you keep it secret and nobody has access to it but you. And finally, and quite relevant to what we heard earlier about those different quantum programming sets, if you will, is copyrights. Any code that you write is automatically protected by the copyrights, and you can further formalize the arrangement. I'm going to further focus on patents. So my presentation is slanted towards perhaps hardware and methods of using the hardware, but I'm touching on software as well a little bit. I want to start with the technology readiness level. This concept was introduced by NASA in the 70s to describe how close to the usability and the new technology might be. So it goes from basic principles observed and reported. In case of quantum, it's been, beginning of the century, I guess. To TRL9, where the system is proven in operational environment, where you can actually put the system on the spaceship and launch it. In the university tech transfer environment, we like to use TRL. This is a proxy for how far a new technology, a new invention is from a product that someone would buy in the marketplace. The interesting thing is that with all those new quantum technologies, especially quantum computing and so on, the inventions span the entire TRL spectrum. It's not just close to the basic research, but also, close to systems proven in operational environment. Here's an example, IonQ, our quantum startup, spin-off from University of Maryland. It's a unicorn. A rather unusual story, but it illustrates some aspects of entrepreneurship and going from the bench, from the research lab, from the bench to offering products and services in a very vivid way. So, short story, a paper is published in 2014 in Physical Review about scalable quantum computer based on trapped ions, right? There was no private seed funding involved in this company. Very unusual. That's why it's a unicorn. And it's basically one of the founders got a phone call from venture capital, the biggest venture capital firm in the U.S. And the person on the phone told Professor Monroe that essentially his Physical Review paper reads like a business plan. And a couple of years later, we have a company that is ready to go public with implied initial market capitalization of $2 billion. And the road to it, I mean, it seems simple on this slide. You go from the idea to building some prototypes and scaling up. But the road of any new company is a long one. And let me illustrate it with this slide, which attempts to capture aspects of IonQ's story. So first of all, it's built on 25 years of research by two very prominent quantum scientists. The first invention was disclosed in 2012, and that invention is what has been published in the Physical Review A in 2014. The company got incorporated in 2015, licensed the intellectual property in 2016, and I went through 2 rounds of founding in 2017, 2019, 20 to the tune of $82 million, and it's now a viable business with over 50 employees, with over $8 million in estimated revenues, and ready to go IPO, which was announced in March via merger with a special purpose acquisition corporation. I really want to emphasize that at this stage, starting with the first invention disclosure to our office in 2012, the company has now 10 issued patents and 70 pending patent applications. So it is important that this is one of the strategies to build a company, right? You build a wall of intangible assets, in this case, a monopoly of ion trapped computing of some type. And I want to talk a little bit more about this specific type of intangible property patents. So in the university environment, we really have 2 situations typically, and I'm speaking from UMD's perspective. Every university would have their own policy. But if you're an undergrad at UMD, and I would suspect this is the case in most universities, if you invent something, it belongs to you, essentially. On the other hand, if you work for the university as a scientist, or if you're hired as a grad student or postdoc, chances are that the intellectual property that you create during your course of work will belong to the university. So the process starts really with invention disclosure to the tech transfer office like ours here at the AMD. We typically file a provisional patent application, and provisional patent application, it has to conform to certain regulations by US Patent Office, but what it really is, it's a placeholder that gives you the priority date for your invention. Because you can only patent things that are not known before. They have to be novel, right? And that's why disclosing to the tech transfer office is the most important thing before you publish. If you publish and then decide that, hey, there's a valuable invention, I want to file a patent application, your public disclosure can and will be used to reject your claims, essentially. Your own publication will be used to reject your own claims, if you will. Typically, the office will analyze the invention and make a decision about patent application. And as you go with this process, the cost is going up, and it's inevitable. On the other side, the value may or may not be created. And typically the value is created by the licensing process. And definitely in the case of universities, even if the scientist who created invention goes and starts a company, since the intellectual property belongs to the university, it needs to be licensed to the company. So the main thing is filing a provisional application before any public disclosure, and working closely with the tech transfer office. Just to give you an example of some of the patents that we are getting at the University of Maryland that have to do with quantum. So here's an example from Professor Hafezi, where he developed those microring resonators on a chip. Again, scientific publication with the invention disclosure to our office before the publication. We filed for a patent application and we've got the patent. He continues to build on his previous work, and now he came up with a way to use those microring resonators as a topological source of quantum light. CMOS compatible silicon insulator technology and potential for creating robust quantum photonic devices. And if you look at different types of qubits, topological qubits are probably least developed at this stage, but perhaps with potential. Another example of a patent, this is a scientist from NIST, is for a method. You can patent methods of doing something, right? So in this case, and again, the pathway is very similar. You do your research, you write a publication, you disclose to your tech transfer office, and if the analysis is thumbs up, resources are invested in a patent application, like in this case, and we have a method of essentially of reading out sensor in a novel, more efficient way, with potential applications in geospatial, healthcare, and life sciences. Finally, software. And when I think about this second quantum revolution, I mean, the analogy I see is and I've been through a couple of interesting revolutions: the PC, the internet, the wireless, and there's some parallels to all those revolutions, right? As an entrepreneur, you don't have to build a quantum computer. Someone did it for you, like someone built, the internet network or the wireless network. So all this infrastructure is coming to life, and the sky is the limit, and your imagination is the limit, how to utilize it to create value. And with quantum, there is definitely a big push to not only to start utilizing those resources, but also in the process develop a quantum workforce, if you will. If you go to IMQ website, I mean, they tell you, hey, get to work, find applications, solve problems, and you can start with almost like fresh, with no hard knowledge of quantum physics or anything like that. Some Python programming skills, maybe enough, or even not that, as described a little bit earlier when my predecessor was talking about the Qiskit. And any software you write is becoming copyrighted the moment it's written. So we probably are facing an amazing opportunity for startups. Just to proxy, the number of patents filed internationally that have to do with quantum, it's going quite exponentially. I just want to click on those two links, and I think I have to switch my sharing. Okay, so this is one of those links from IP Watchdog, and notice the exponential growth in number of patent applications. And we have qubits, we have hardware and application all going up exponentially. And then if we go to the second link, and let's make sure that it's visible. This is a quantum computing patent families by qubit type. And if you look at topological qubits, and I gave you just one example before, this is a relatively new field. While if you look at superconducting loops, obviously you can imagine that Google and others have a very healthy share of those patents. Ion trap, good portion of it is IonQ actually. All right, we have still a couple of minutes left, so let me continue and wrap up this presentation. So how you should think about approaching this opportunity. And by the way, I mean, the best time to think about starting your own business is probably when you are, close to the university age. You don't have as many obligations as later in your lifetime. I joined Quantum 4D, which had nothing to do with quantum, at much later stage of my life, and that was an interesting ride. But how you should think about approaching the opportunity? Well, first of all, build quantum skills. And it doesn't mean that you have to become a quantum physicist, not at all. But let's say you are in finance, right? Studying finance, and then just having a little bit of grasp on what you can accomplish with quantum computing might make you incredibly valuable resource for a big bank, for example, if that's the pathway you are thinking about. Or maybe you will be able to create a company that has to do with something financial, because you understand those aspects. But the key, except of skills, is really identifying the problem that can be solved, or identifying an unfulfilled demand in the marketplace. And great mechanisms for it, such as I-Core, which forces you to talk to potential customers and validate your hypothesis about the value of your potential product to some customer segments. And once you have this idea, and then supporting tech, and then this technology is protected, you need to build a passionate team. It's not only about technology and product development, but also the business team. It's not very frequent that the technologist is also the best person to run the business. All the mundane stuff that has to do with payroll, HR, things like that as the company grows. And the most important, you need to secure funding, which is the third T, in the form of R&D grants, commercialization grants, and private investment. Most importantly, you have to move fast, be nimble, and adapt to customer needs. So, that's probably the closest to the recipe I can offer you if you think about starting a business. Finally, whether you are successful in this startup business or not, you will build a very valuable set of skills. I mean, if you open here a couple of titles, and I really like this quantum Washington dollar kind of combo here from The Economist. But I mean, Accenture, Forbes, The Economist, McKinsey, everybody's looking into this. And a good chunk of what they are looking at and analyzing is the workforce. So what is a better way to build a very tangible skill set, if not through attempting to build a business? And I will wrap up with that, so we have a couple of minutes for questions. Thank you very much for listening.
Thank you, Piotr. Great talk. Thank you. Now it's time for Q&A. Do you have any questions? If you have questions, you can just unmute yourself and ask, or put a question in chat, either way.
Hi, Piotr. This is Hina from Mason. I have a question. So you mentioned that IonQ had already have the 10 issued patents, and then I see that in a very short span, say from 2016 or 17 to now, they have about 70 pending applications. So I'm just kind of curious to know if this all new patents were based on the prior kind of the technologies, or is it also a result of a lot of their R&D that went in after starting the company?
So majority of those patents and patent applications are based on invention disclosures disclosed to our office after the initial invention disclosure in 2012. Part of the reason IonQ can frankly afford such an investment in intangible assets such as patents is because they've got a substantial private investment. There's no way in the world that University of Maryland could support that number of patent applications. It's simply, the budget is not there, and when we make decisions, we try to make optimal decisions, and obviously the first patent application was a good decision, but all the rest of it is resulting from research that is done at the University of Maryland, at Duke, and also within IonQ. Most of those are still joint properties, and I bet that as we go, IonQ will continue building their patent portfolio and with less and less input from the university. However, I mean, Professor Monroe has dual appointment both at the University of Maryland and at Duke, and he has research groups, and I'm pretty sure that new inventions will be coming from the universities as well. So it's a collaboration process.
That makes sense, and congratulations once again for this remarkable success.
Piotr, I have a quick question. So just wondering, as you're named a bench to billionaire or millionaire, how many of the startups end up being a billionaire or millionaire?
I'm not sure if I follow your questions.
Like the successful rate of the startup.
Well, that's got to be crazy low.
Just in general, for startups, the success rate is very low, and also it depends on the definition of success, right? I mean, a profitable, sustainable business is a success in my opinion, right? But I wanna, so just in general, for startups, success rate is low, meaning they disappear from the scene, they get dissolved one way or another. And quantum will not be any different from that. The big advantage of starting a business within a sort of a realm of university or spinning off a company based on your research or somebody else's research with whom you work in the university ecosystem is the amazing support you are getting, and also certain types of funding that is available to university spin-offs that is just not available to entrepreneurs who are not affiliated with the universities. And I'm sure that Julie Lanzer will talk quite a bit about the entrepreneurial ecosystem and the newly formed Quantum Startup Foundry. But just to mention a couple of things, right? If you are a university-based entrepreneur, you have access to resources like ICOR, where National Science Foundation will pay you money to go visit and talk to your potential customers to validate your business hypothesis. R&D grants, in case of IonQ, we're talking 25 years of research and tens of millions of dollars in research grants, but this continues with SBIRs, STTRs, and so on and so forth. In the state of Maryland, we have a number of commercialization grants through TEDCO, and and then the network of angel investors, such as Dinkman Center Angels at the University of Maryland, and just this support structure to help a fledgling business to get off the ground is just amazing in the university setup. So bottom line is the probability of a success of a startup that's spinning off universities is probably substantially a couple of orders of magnitude higher than for non-university startup.
Thank you, Piotr.
Thank you.
There's a question in chat, maybe a naive question, but it's the concept of the parallel processing relevant in quantum computing.
Could you repeat, please?
Okay. The message sent direct to me, so you probably not see it. Let me forward it to the chat so you can see. It's I guess this question is not for this session, right? It's the concept of parallel processing relevant to the quantum computing or not.
My uneducated guess would be absolutely yes. I mean, I've read an interview with Chapman, who is the CEO of IonQ, and he was talking about putting quantum acceleration devices on the rack in some server center, whatever. I don't remember the exact details of that comment from the CEO of IonQ, but that makes me think that the sky is the limit here.
If I could, I would just. Yeah, if I could just, this is Julie Lenzer. I think I'm on the agenda next, but in reality, quantum computers, the architecture is so different than conventional computing that it's hard to draw strict parallels. But as far as being able to like put computers in like serial or to kind of do distributed computing, that's probably more likely. The way that the qubits work is that they actually do hold multiple states at once. So in essence, you can do parallel processing within a qubit, right? Yes. So it's hard to compare because they are so different architecturally. But it will blow away parallel computing on traditional computers from an ability to solve big problems.
But there's definitely a notion of distributed quantum computing. Right. So using multiple machines, especially if we make progress in quantum networks.
Yeah,